Welcome to the water quality installment of the Premise Plumbing Modeling webinar series. I'm Jonathan Burkhart, and we'll be moderating today's session. Last month's webinar focused on hydraulics, which helped to predict how water moves or behaves while in motion. This month's webinar highlights water quality, which can be impacted by both moving water or periods of stagnation. Water in home and building water systems is likely to be stagnant the majority of the time, highlighting the importance of modeling these periods in addition to periods of use. Even during periods of use, any unused branch within premise plumbing systems remains stagnant, which results in multiple water quality conditions within a building based on use history and other factors. During the demand estimation webinar, issues associated with predicting water quality usage patterns were discussed, and during the water age webinar, the use of water age as a surrogate measure was discussed. As we've seen previously, capturing the complexity of premise plumbing systems requires tools and approaches that account for all of the characteristics of these systems. If you are unable to attend those past webinars or would like to review their material, the recordings have been uploaded to YouTube and a link is available in a periodic flyer associated with these webinars. Today, we have 4 speakers who will present on a few topics associated with water quality modeling and its issues. Following their talks, we will have about 30 minutes of questions and open discussion, but please feel free to use the chat feature to ask questions during the talks. These will be addressed in the chat or after all the talks have concluded. And again, a reminder to please mute your mics and turn off your videos during the presentation period. And a recording for the sessions will be uploaded to YouTube, and this typically takes about a week. And I'll turn this over to Tim Bertrand for the first talk.
Thank you very much, John. I'd like to thank the organizers for the great webinars thus far. I've certainly learned a great deal, and hopefully I can make a small contribution today. I'm Tim Bertrand. I work with ESPRI, and today I'm taking on both disinfectants and pathogens, so buckle up. I've tried to focus the presentation, as John was saying, on what happens during stagnation. Other presenters have done a great job of talking through what happens during period of flow. And also from a modeling perspective, what's in the pipe after stagnation, you can think of as initial conditions for your periods of flow. So this is me trying to help out. I left a bunch of slides on the cutting room floor. I included them as some bonus slides at the end. So those will be, I think, available on a SharePoint site or somehow, even though I won't be able to talk through those today. I'm going to start with acknowledgments. The data in original modeling that you see in this presentation were all generated in a US EPA project. And the lead institution on that was Drexel University, Colorado University Boulder, and ESPRI were also involved, and you can see quite a number of people contributed to this. What I'd like to cover today, first I'm going to give you an orientation to water quality modeling for building water systems. This might be gratuitous or unnecessary, but hopefully it'll set the stage for my talk and the upcoming talks. Then I'll talk through disinfectant residual in the buildings, what practices community water systems currently use, and what happens on the building side of the meter. And I'm going to try to highlight what is different in the building compared with the distribution system. And then I'll just touch on pathogens in buildings, but I can assure you that there are a couple of really nice presentations that are going to do this topic justice. And then I'll revisit the key points. So from my perspective, the high quality water at the tap, we talk about source to tap, but in reality, the community doesn't quite get the water all the way to the tap, and that is the modeling community as well as the community of people who need to have safe water all the way to the tap. Here is a schematic that I've used in another study showing what happens to the THM concentration as you go from the source all the way to the tap. You have a significant increase during treatment. There is another increase during the residence and the distribution, and then there is a significant increase, and it could be as much as 100% increase in THMs depending on conditions within building water systems, and it's the final product at the point of use that people are exposed to. And so I'm thinking of the partnership between the water supplier, who provides the water that has some THMs in it and some conditions that could lead to further THM formation, and the people who operate the building water system. Key differences between distribution systems and building water systems that are important in the modeling. In most building water components, flow is intermittent. You've already heard about this. You can think of building from a reactor modeling perspective. Building water systems are generally sequencing batch reactors, and they require different models than a fully flowing system. Each stagnation period begins with a stock of compounds and organisms. You build up manganese, you build up TOC, you build up organisms, and those are the beginning point for the next period of stagnation. So there's hysteresis in the system. Temperature is different in the building water systems compared with the distribution systems. Cold water eventually gets to room temperature unless you do something about that, and non-circulated hot water, the same thing. Pipes are smaller and made of different materials. You'll see the profound impact that has on disinfectant demand and decay. And then there are fittings and fixtures that need to be accounted for. All right, so building as a sequencing batch reactor. If you think of a zero-dimensional model, you've got things that come in the water supply. There are pathogens, disinfection byproducts, taste and odor, manganese, iron, organic carbon. There's probably no lead in there. And you've also got additives and other, not contaminants, but other constituents of the water that impact what happens in the building water system, and particularly the residual and the corrosion inhibitor. During residence in the water, you develop what I'm calling the building water system surcharge. You change some of these contaminants in concentration. And so our job is to think about where those changes take place and how to control the ones that need controlling. So kind of focusing in on control, my objective in modeling is to think about what efficacy control techniques can bring, or what improvement control techniques can bring. So I made just a simple schematic identifying where you might implement controls. You can implement controls on the building supply, which would reduce or postpone intrusion, particularly of microorganisms into the system. Things like UV or filtration, but be careful not to lose all the disinfectant residual when you do that. In the cold water plumbing, flushing is a great thing to do. In previous presentations and discussions, I'll name a couple of names for good reason. Jim Lutz and Gary Klein both are very cognizant of not wanting to waste water and energy, and that certainly is a goal as we think about how to better operate plumbing systems. But flushing really can do something nice, which is to clear out bad water and avoid exposure. So maybe we can think of not necessarily wasting water, but using water to our best advantage in flushing for cold and hot water as well. We can select pipe materials, maintain a residual, and do periodic treatment for biofilm control. I won't go into the water heater because that's a whole topic unto itself, but that's certainly an opportunity to control water quality. You can control water quality, at the shower head. Not in every case, but in many cases, the very last leg of plumbing is potentially the most problematic. So paying specific attention to that leg could be a beneficial strategy. So ESPRI's top 4 water quality modeling needs. Hang on a second. Sorry about that. In applications, I say ESPRI's because we're focused on water quality. If you were coming at this, like NIST does from thermal science and energy efficiency, they probably have 4 different needs. But our needs are first, building-specific flushing and first-use diversion strategies. First-use diversion, this is something kind of new. I'm a proponent of, if the water quality is very poor in the very first couple liters of water, let's divert that from people being exposed to it. So flushing strategies, pardon me, that reduce the contaminants to a target level. You have to model the dispersion and hold back in tortuous branch systems, mixing with dead legs and phenomena that Ian is going to be talking about to some extent later. The second modeling need is disinfectant fate and transport. Pennsylvania right now has a proposed rule in front of the legislature, in which they are suggesting, I need to read through the rule more carefully, but they're suggesting that building water systems need to maintain 0.5 milligram per liter of free chlorine everywhere at all times, or 1 milligram per liter of chloramines anywhere at all times. That is there's a desperate need for modeling to figure out how to do that. The EPA net has been used to great effect in distribution systems to figure out how to maintain residual. That type of ask that Pennsylvania has now, and this is just a proposed rule, not a final rule, will absolutely require modeling and strategies. So disinfectant state and transport, particle and biofilm detachment and transport. You're going to hear us talk about that in a little bit. And really generally, the impact of control strategies on microbial ecology, all the way to distal taps. When Michel Prévost was in the inaugural webinar was presenting in the inaugural webinar of this session, or this topic, she said that we really do need risk models, and I would agree with her. And I'm not as much interested in predicting the magnitude of risk, but looking at the impact of control strategies on risk and thinking through how to operate and design systems better, and using modeling to help us get there. All right, so that's kind of the philosophical part of the discussion. Now I'm going to get into secondary disinfectant. The water supplier residual disinfectant practices are critically important to know because they set the stage for the modeling that needs to be done. They also determine how likely it is that certain opportunistic premise plumbing pathogens are in the treated water. It's not for sure, but there are indications that the selection of disinfectant that will determine the likelihood, for example, that you have either Legionella or mycobacteria in the building supply water. So the water supplier disinfection practices are important to know in that respect, and they also determine the behavior and the potency and the chemical properties of the disinfectant in the building water system. It's no surprise to anybody on this call that chloramines and free chlorine behave quite differently. Why we want to model the disinfectant? They're one of the 3 critical tools in the controls inventory, the other 2 being flushing and thermal control. We don't have a full understanding of their performance, and modeling is a great way to explore conditions and models or conceptual models that will help us understand them better. How effective are they at biofilm penetration? David Wallman has published some really nice studies on that, but they are empirical and doing some modeling studies using results that he and others have published on penetration would be great. We can answer a question, for example, is there a minimum residual concentration that has to be maintained? This is a really big ask, and knowing whether maintaining a minimum residual is necessary, or what that residual is a very important modeling question. And then how does temperature impact the residual requirement and vice versa? Do you need the same residual in 45-degree water as 25-degree water? The answer is probably no, but getting more specifics on that would help. Disinfectants also play roles in processes other than disinfection. They play a role in passivation and corrosion, and disinfection byproduct formation. So I'm going to show just a few results from pipe rack studies that were done at Drexel and Colorado University Boulder. There were cold water and hot water studies. I'm only showing the cold water study results today. The experimental factors, there were pipe racks set up in Philadelphia, which is a chloramine supply, and in Boulder, which is a free chlorine supply. And the pipe racks were identical. They were 3 materials, PEX, chlorinated PVC, and copper. 2 diameters, 1/2 inch and 3/4 inch. We used the pipes 2 times per day for half of the pipes and 1 time per week for half of the pipes. There were duplicates for each of these factor sets. And the building water source was different, as I said, 1 chloramine and 1 free chlorine system. The analyses that we did on the data, we looked at basic water quality parameters, including the disinfectant residual concentration, microbial parameters, Legionella that we never found, NTM, Pseudomonas aeruginosa, free-living amoebae, and thermotolerant free-living amoebae. And we found all of those except Legionella at the Philadelphia site. and none of them in the free chlorine site. We looked at disinfection byproducts and also metals. All right, this is, I'll explain the figures on the right first. They're a little bit hard to process at first, the heat maps, and then I'll tell you what they tell you. These are results of of disinfectant residual. The heat maps show the disinfectant residual concentration over time. Sample round, you can think of that on the x-axis is the time. Each of the sample rounds in this study went on for about 9 months, and then we took additional data that aren't shown here. The sample round or time is on the x-axis, and each of the rows, it corresponds to one of the combinations of pipe type and diameter. The very top row shows the feed concentration for the pipe rack, and we collected the feed concentration after flushing the line ahead of the pipe rack feed for, I don't remember how long, but long enough that we thought we were pretty close to the water in the main that was supplying the building. On the free chlorine rack, the heat map on the left, you can see the light colors, that yellow color, there was no residual in the copper pipes ever. And this continued on for 2 years. We expected demand on the copper pipes for some time. We did not expect it to continue on for 2 years. And this is the residual after only 12 hours of stagnation. We saw a significant decrease in the residual for over 12 hours for all of the plastic pipes. For the chloramine rack, you can see that we started with a really high residual. They were getting, on average 2 parts. And within 12 hours, we saw that decline to, less than half in most cases. We saw that there was a little less left in the copper pipe during the early going and even some of the late going. And there is clear and multiple lines of evidence that nitrification, persistent nitrification, 365 days a year was happening in the chloramine pipe rack. A couple of quick thoughts on chemistry and modeling for 12-hour stagnation residual concentration change. On the x-axis of the plot, again, we see the sample round, and we see that the free chlorine concentration or the change in the free chlorine concentration on the y-axis. The feed water residual is shown as solid black squares, and then residual in control samples. These are samples of feed water that were kept in the dark in amber bottles and measured after 12 hours are shown in the open black squares. The residual coming out of the 1/2 inch and 3/4 inch PVC pipes, the change over that 12-hour period is shown as the 2 different colored, the green and kind of blue dots. You can see that there's somewhat greater residual loss in smaller diameter pipes than large diameter pipes, and that there was significantly greater residual loss in the pipes compared with the control samples. This is not new or surprising, but it certainly is very direct evidence. Number one, that the modelers need to consider the pipe wall effects when they develop the models for the building water system residual, and that pipe diameter is indeed very important, particularly during these periods of stagnation. One other plot on the subject, we looked at total THM concentration over 12 hours and 1 week, and I'm showing results for PEX pipes 3/4 inch in the plot on the right. Again, sample round, which is time, is on the x-axis, and the change in the THM concentration, either over a 12-hour stagnation period or a 1 week stagnation period, is shown on the y-axis. The 12-hour control, the amber bottle that was kept in the dark for the change in THMs, is shown as open circles, and the filled circles show the 12-hour results from the PEX pipes, the 3/4 inch PEX pipes, and you can see that there was a bit more formation in the pipes than in the control sample for 12 hours. For 1 week, that trend flips. The filled squares, red ones, are the pipe concentrations and the pipe delta THM over that period, and the open squares show the control, and the situation flipped. What seems to be happening is that there is THM formation near the pipe wall. There's different TOC in the pipe, and So there is a different, it reacts differently with the chlorine that comes in the very near term, but you exhaust the chlorine faster, and ultimately you can form more THMs if you outside the pipe in the control. So the take homes for disinfectant modeling. Disinfectant type, initial conditions, and boundary conditions are going to vary widely among building water systems. Demand and decay models have to be reparameterized. The models that exist in EPA right now need to be reparameterized for copper catalysis, need to consider that there's different organic carbon and constituents exerting demand, and that there are different surface materials. Last thing, nitrification is highly likely in building water systems, and it's probably present 365 days a year, and in many cases, nitrification is likely to drive the residual behavior in the system. All right, real quick through opportunistic pathogens. The whole process of pathogens, of pathogen exposure going all the way to a person. First, there's inoculation of buildings from the building water supply, and there's ample evidence that low levels of ops are generally present in building water supplies, and the water is not sterile. Once in the building, each use of a particular pipe component or of a particular component is a chance for the pathogens to become established in that component. Once established, there's going to be some growth, or there could be, and the growth depends on what was left behind in the prior period of flow, how long the stagnation occurs, and the temperature and disinfectant concentrations, which change over time. To get to points of use, the pathogens need to be sloughed or eroded, and then carried by advection and dispersion. They might be inactivated on the way to the points of use. And then at the point of use, I think Carrie is going to cover this in some detail. Exposure ultimately involves getting all the way to the person and overcoming all of the barriers in place. Intrusion, really quickly.
Hey Tim, I hate to interrupt.
Yeah.
If you could wrap up in about 2 minutes so we can fit in the other presentations.
I'll do. All right, and I'll leave this for further reading. Intrusion, there's ample evidence that the pathogens are in the building water system, and there's a few studies for you to read if you're interested. And there's really no great modeling approach out there, so I made a couple of suggestions. Intrusion can go deeper into the building water system. If you think that the water heater is a barrier, you're raising the temperature of the water and you're killing pathogens before they go in deeper into the water system. That might not be the case. There is short circuiting that happens at water heaters, and so pathogens that you thought were being exposed to 60-degree water might not be. And this is a great opportunity for modeling, and the Lagrangian particle tracking that a previous presenter talked about would be a great approach here. In growth, we see that microorganisms here on the plot shows microorganism concentration, or NTM concentration, over the study period in the cold water pipes or PVC pipes. The red pipes, or the red solid line is large diameter high use pipes. The blue solid line is large diameter low use pipes, and you can see that there's somewhat different behavior between the high and the low use pipes. What we're actually seeing is a growth and flushing process that I'm depicting on the right hand side. And so that knowing that process is the process that's taking place tells us what control strategies we need to use. And Legionella pneumophila is going to be more complex. I'll attribute this scenario to Marc Le Chevalier. It's possible that there is this complex ecology that happens, and that in the early parts of stagnation, free-living amoebae prefer to ingest something other than Legionella, and as they run out of the other food, they might ingest Legionella that could then multiply. So takeaways: residual disinfectant. The disinfectant demand and decay change when the water moves from the distribution system to the building water system. This was something that was known. Just wanted to bring it to your attention to improve the modeling efforts. And nitrification is something that does need to be modeled or at least predicted because it's probably widespread in buildings with chloramine supplies. The premise plumbing pathogens, new water is good and old water is bad. I'm a fan of flushing out at least the minimum amount of water to get that good water in there. There is hysteresis. You can build up a stock of organisms, and there are several studies. Collins out of the UK had a nice one showing that the occurrence of Legionella is more common in older buildings and older fixtures. So that supports that you are really building up a stock. And control system design needs to reflect the system hydraulics, and that relates to thinking through the dispersion in the system and particularly what happens in storage. And with that, I will turn it over to the next speaker.
All right, so thanks so much for having me. I'm Carrie Hamilton. I'm from Arizona State University, and today I'll be talking about a preliminary risk trade-off model that we're working on for optimal water heater temperature that accounts for energy costs, Legionnaire's disease, and scalding. So I think we know from all of the talks that we've heard so far in the series that premise plumbing modeling is complex, and it makes it very difficult to choose an exemplary situation to model if you're working on a generalized model. And Tim set this up very nicely for me today in that, I'm going to focus on the water heater and break down some of the decision elements that we have related to that. I want to highlight here that I'm going to talk about a subset of water quality considerations, but clearly there are a lot of different water quality considerations when it comes to premise plumbing, ranging from microbial to scalding to chemical contaminants, and also costs for facilities managers who have limited resources and bandwidth to address all of these concerns at once. So we think that there may be trade-offs in some cases between some of these risks, and having a formalized framework in order to deal with some of these things is certainly an interesting way to go about them. So we decided to focus on the hot water heater and recirculation loop in our model, because we know that the hot water system can be a contributor to water quality issues, and I'm thinking particularly about Legionella growth and some work done at Virginia Tech, and also a recent simulation model on Legionella risks in relation to different parameters done by Wang et al. In Environment International. And there really just aren't, there's a limited number of levers that we can use to control microbial water quality, and temperature is a key one of them. So we're going to highlight that today. On the left side of this graph, I think everybody on this call is very familiar with the public health importance of Legionnaire's disease and Pontiac fever. But I think probably there's less familiarity with scalding due to tap water in the US, and there's really limited data on this. So we did find some data, and there is some presented in the National Academies of Science, Engineering, and Medicine report last year that there are scalds reported in the US, and some very small subset of that is due to tap water scalds. And it's really hard to exactly determine what the cause of some of these scalds are. And in some cases, they have been suspected in abuse. And the reason why some of the data we have on this is a little bit dated is these types of data are not collected anymore through the Consumer Product Safety Commission. So clearly, we have a different level of evidence for these two different types of risks. In addition, the National Academies recommended a set point of 60 degrees last year in their report, and there are some other water heater set point recommendations out there to try to conserve energy and also reduce the risk of scalding. So it's not that this is the only decision that needs to be made in the premise plumbing environment, but this is a way for us to look at different trade-offs and play out how different controls might interact in the system. So I have to highlight here in developing these three different submodels for our larger decision analysis model, my PhD student Ashley Haida is working on this, and this is really a wonderful effort on her part, so credit is due to her. In the preliminary model form, we track a lot of different parameters throughout the system using a series of differential equations, as well as conducting Monte Carlo simulations at each time step. And we get down to our final outcome, which is our optimal water heater temperature. However, we track a lot of different parameters throughout the system, so we focus on tracking temperature, chlorine residual, biofilm sloughing, Legionella concentrations, and growth and activation of that Legionella. So this is quite a bit of data that we're collecting. We implemented this in a machine learning framework in Python known as PyTorch, and we're not making use of necessarily all the machine learning functionality right now, but it is set up to go in that direction. It uses the same ODE solver as ODE45 if you're a MATLAB user. So the benefit of this is that we can use this modeling framework to ultimately learn real-world data and hopefully use that in some monitoring information that we have at ASU right now. It makes efficient use of computing space, and the benefit of this is that it's easily scalable to large Monte Carlo simulations. So how do we choose our schematic that we're going to work on? Here we've chosen a clearly very simplified system as a starting point for this model, and we're in the early stages of developing this. So if we have water coming in from a main line into a heater, we chose something that would be similar to a hospital room schematic here and just focusing on, one line ranging from the recirculating loop to the shower head. So I recognize this is maybe not 100% realistic system, but the point of this model is that this can be adapted to a variety of scenarios. We also here have not considered the contributions of the cold water line right now. We have not assessed thermostatic mixing valves, which clearly are very important components of the system. So this is really to get us started in getting the computational framework in place. We separated the water heater into a series of nodes, which we were then able to model heat transfer into and out of according to when a heating element in the water heater is on or off. So, that is accounted for throughout the model, and water coming into the main line is accounted for, and temperature is tracked throughout the system. We also account for heat loss in the pipe sections. We are considering plug flow throughout the model, which is a simplified assumption. So you could certainly consider other hydraulic models when you're doing this and integrate that in. But for the purposes of this example, that's what we chose to go with as a simplified example, which we felt was appropriate given the flow conditions of the system. So our first submodel is our Legionella pneumophila infection risk model. So this makes use of quantitative microbial risk assessment, which just relates some exposure concentration in the environment to a probability of getting sick or death. And you'll notice that as Legionella pneumophila is generally contracted by inhalation or aspiration, that the aerosols that are generated from different fixtures, if we have smaller diameter aerosols, we see our risk arrow going up to the right there, because as the aerosol gets smaller, it can penetrate deeper into the lungs and arrive at the alveoli for initiating an infection. So we have a series of exposure equations to model, the partitioning of the bacteria and aerosol, the removal of the bacteria in a shower environment where there's ventilation, and I won't go into all the parameters here, but I'll just highlight that we are putting all of these risks into a common currency using something called a VSL, or value of a statistical life, which is not literally the value of a person's life, but perhaps we think of it more as, given scarce resources, our rate of investment to avoid a statistical case of illness or death, etc. We were able to look in the literature and look at various temperature windows and derive kinetic rates for growth or inactivation, depending on the particular temperature in the system at that point. And, we were able to apply these kinetic rates at each time step throughout the model. Tim mentioned the importance of biofilms, and I emphasized that here. We accounted for sloughing by looking at sloughing rates from the biofilm to the bulk water throughout the system, and treated the kinetics of those differently, as the sloughed biofilms are likely to have a bit more protection from disinfectants. And of course, both grow or inactivate at particular temperatures. So we account for inactivation due to remaining chlorine residual, due to temperature, and we account for degradation of the chlorine as well. For sloughing, we do account for sloughing rates, and I won't go through all of these different parameters, but we take into consideration the mass of the biofilm at different points of the system and use decay rates from a recent model that looked at the impact on sloughed biofilm versus planktonic Legionella. I'll just highlight very briefly that when it comes to the dose response model, the missing piece or function that describes the relationship between what you're exposed to and the probability of some adverse effects, that there is more than one choice available. And, one is sort of a less severe outcome and the other is a more severe outcome, and that tends to have a large impact on projected risks. For our scalding risk model, we looked at the very limited data that was out there on scalding of skin, and there's a 1940 study by Moritz and Henriquez, which was probably, before modern IRB times, where humans and pigs, live humans and pigs, were scalded, and then a curve was developed with these data. So we were able to get some data. They presented data from both pigs and humans, and the human data did overlap with the pig skin data. So we were able to read data and fit functions to these curves and then use them in our model as thresholds for the amount of skin damage, and then apply costs for those based on literature data and insurance reports that assign costs to different types of medical visits. And then finally, we have a very simplistic energy cost model where we calculate the amount of heat necessary to heat the recirculating loop and the water heater over time and apply cost to that. And all of these things are normalized on a cost on a daily basis, so one shower happening over that time. So getting into our results now, and this is kind of the guide for our results, is that the premise plumbing situation that we've chosen is divided into different nodes, and I'll mark those on the various graphs. This is kind of a key to interpreting those. So my water heater is at the bottom from node 0 to 10. My recirculating water line is from node 15 to 35, and my branching pipe is up at line 40. I'm sorry, the hot water goes until 40. So we're able to look at temperature changes, for example, what I'm showing here throughout the system at the different nodes over time. And this is modeled for a 24-hour stagnation period since the previous shower, and we did a 100-second initialization period in this model. We use a little bit faster of a method to calculate what was happening over the 24-hour period. And using this method, we look at a set point of 48 degrees Celsius, and we can see the most important thing here. We see moderate temperatures throughout the system, but mostly that if we look at the right plot here, our chlorine concentration is plotted, and if we look at 40, node 40, that is the one closest to the point of use. So we're really not getting very much chlorine to the point of use for a shower. And this is accounting for if someone were to turn on the shower and jump right in, but many of us might wait until the shower warms up. So that's certainly not, considered here, but it's something that could be added to the model. Getting into the Legionella results, example results, as this will certainly give you a lot of information. For a set point of 48 degrees, we see that, you are getting some sloughing throughout the system. The concentration of Legionella in the bulk water, I'm considering the slough in the bulk water and the planktonic Legionella to be separate fractions here. So my planktonic Legionella has much less of a contribution than my biofilm does, than the sloughed biofilm. And the graph on the right here is what's remaining in the biofilm. So it does decrease as the slough happens. So we can look at the relative fractions in these different components. If we were to compare different set points, I know there's a lot on this slide here. So the main thing to note is that we see that at the higher set point, the temperatures are higher, more red throughout the system on the most left-hand, bottom left graph there. And additionally, that our Legionella concentration is decreasing at the set point of 60. So we can see that happening in the darker blue colors in the center Legionella plot for the 60 compared to the 48. Now, if we look at our total cost plot, so what we did is we computed a total cost at each set point, which is our infection cost, our energy cost, and our scalding cost, and then we can calculate the minima for that over the entire range of set points. So in this case, if you use the median of the total cost as your guide, then you'd be leaning towards more like a 48-degree set point, which is on the lower end of things. But we'll notice that our confidence bands, depending on which dose response model we use, so our subclinicals on the left and our clinicals on the right, that our infection bands can be quite wide compared to some of the other bands. And at least, this isn't necessarily all the time, but at least for the scalding situation that we've modeled, it doesn't start to be an issue until we get to an extremely high set point, which no one probably would really use, of 62 degrees, where we see a jump up there, if we consider our necrosis and other endpoints. So we didn't consider the redness of the skin as a relevant endpoint, as that wasn't thought to be associated with a cost or a medical visit. But certainly if you had more of a gentle gradation in your scalding considerations, perhaps you would see that scalding cost come up a little bit higher. So I won't have time to show you all the sensitivity, of these different parameters, but I'll just highlight that you can play with different parameters in this model, and that, for example, if we were to increase the pipe length of the system, if we just look at our 60-degree set point, the 2 rows on the bottom, and you compare, our Legionella concentration certainly goes up as the pipe gets longer. So if you just look at the slough concentration, it is a lighter yellow than what's on the bottom. So if we were to make a longer recirculating pipe, we would certainly start to see effects to the Legionella. So this is nice because, we've developed this framework for rapidly and relatively realistically evaluating different configurations of the water heater, of the premise plumbing. Of course, we can improve the hydraulic modeling portion of this to be a little bit more sophisticated, a little more specific to the system that you have in mind, but we think it's a really good start on the framework here. And this corresponds roughly with our knowledge of hot water systems, but of course, we need to take some data, which we're planning to do, and do some parameter tuning. So up next for us, I'm sure you could make a list a mile long of additional things that we could consider in this model, but the thermostatic mixing valves are certainly at the top of our list, and modeling the impacts of the cold water line, looking at some more nuanced characteristics of biofilm sloughing rates, et cetera, especially under stagnant conditions where we have more sparse data. And then hopefully, making this model into an adaptive framework where we can learn data from different buildings and then perhaps arrive at, maybe a little bit more generalized of a calculation. So I'll just sort of leave with this last thought, which is that, the set point is just one tiny little decision out of all the decisions a facilities manager has to make. And we just considered Legionella, but there probably is no universal best set of conditions that's good for every pathogen, for every contaminant, for every single situation. But, given the regulatory importance of Legionella, there's reason to focus there. And certainly we could expand this model to look at other risks at the same time and evaluate trade-offs among different types of design or operational decisions. So I think that brings me toward the end of my time for today. So I just want to thank you all for tuning in. And if you'd like, please feel free to reach out if you'd like to discuss this further. Thanks.
So yeah, our next speaker is Ian Geimer, that will revisit some work with dispersion from last month's hydraulics, but with a water quality focus. So on to you, Ian.
Okay, so thanks for the invitation, and I suppose to try and put this piece of work into context, what I'm probably going to talk about is the link between the hydraulics that was covered in the last set of seminars and the water quality, the risk issues that are covered in this one. So I'll give you a bit of background because I'm personally new to this group, and give you a little bit of explanation about myself. I'm Professor of Civil Engineering at University of Sheffield, and in 2018 I received a fellowship which allowed me to play at looking at mixing and lots of different things, and my area of interest is doing lab or field measurements. And I got onto this piece of work basically because I wanted to simplify some urban drainage modeling challenges that I had when we're having time varying flows, accelerating, decelerating flows due to storm events. It was causing me a problem in my analysis, and so I wanted to reduce the effect of changes of volume of the system. So I thought, well, let's go right back to the pipe work. I can change the flow, I can change the acceleration without changing the volume. So that's how I got into this. And all the work that I'm going to present here was done by James Hart, who was a PhD student at the time at the University of Warwick. He's now a lecturer at the University of Coventry in the UK. And so I've tried to pull this together, and I thought my title was a bit presumptuous. So I decided that I really should clarify that and suggest that we're only going to look at some of the limitations of Taylor's work. Excuse me. And so why should I feel that, I have I'm in the position to question Professor Sir G.I. Taylor, FRS. The work's been cited so many times that it's taken for granted. But what I'm assuming here now is that most people have listened to or watched or are aware of this work, and Feng Chang's presentation of a month ago was very useful in setting the scene. So I'm not going to go back on the original assumptions and things. I'm just going to quickly illustrate what was published by Taylor. In 1953, he started off because he was asked to look at how vaccines spread in blood. And so he then went on to publish this paper which discusses how material spreads in laminar flow and gives the equation down the bottom that the dispersion coefficient is a function of pipe diameter, velocity, and molecular diffusion. He then kind of extended it to look at turbulent flow and came up with an expression that covers the longitudinal dispersion coefficient as a function of pipe radius and bed shear velocity. And this is used in nearly all water quality network models, and whether that's for large systems, for long periods of time, that's fine. When we start trying to nudge the kinds of boundaries and the applications of this, then we come up against some limitations. And what we tend to do with his work, if we're doing measurements, is we'll undertake a series of measurements whereby we have a tracer in a system, and we'll measure the concentration distribution at different locations as the tracer is passed through the system. This is a plot from data from James's work when we were using rhodamine in a pipe. The pipe system was 25 mil diameter pipe and 13 or 14 meters long. So it's even more simple than Kerry's previous example of a pipe. And so what we did initially was to look at what Taylor had done, and I'm not sure you can see, hopefully you can see my mouse on the screen. And the top right hand corner is a collation of previous data. And you'll see we've highlighted Taylor's data as a red diamond here. And you'll notice there are only 3 points. So the amount of data you need in 1953 to get a paper in the Royal Society is 3 data points. And to fit to those 3 data points, the analytical solution is a highlighted dashed line there. And you'll notice that a lot of the data that's been collected by other people doesn't fit this dashed line. This is still in the turbulent or the transitional zone and doesn't fit Taylor's model because Taylor's model doesn't account for shear effects near the pipe boundaries. So to start off looking in our system, James undertook a series of tests here, and these tests you can see that they don't quite follow Taylor's model. Really depends on the hydraulic characteristics of your pipe, but there is a reasonably good trend that you could take which will cover both transitional and turbulent flow situations. And this work has been published in ASCE Journal of Hydraulic Research in 2016. So that covered the kind of transitional and turbulent flow situation. And then we've got this laminar flow condition down the left-hand side of this plot. And as Feng Zhang said in the previous presentation, that for laminar flow, we've got an equation that Taylor gave us, a squared u squared 48 dm, and it's valid given enough time. And Feng gave a nice presentation and a calculation of that for a certain size pipe, and my suggestion suggests it's kind of, that's okay, it fits. You can model it with a Gaussian distribution if it's in there for more than 8 hours. And so I suspect in building or premise plumbing that 8 hours of moving at constant velocity is unlikely. You've then got work from other people. So Phil Chatwin in 1970 said, well, that might be an underestimation. It might be 10 times more than that. So it gives up to 80 hours. And Wu and Chen in 2014, again, said, depending on how accurately you want to model this, it could be 100 times more. So whichever way we look at it, we've got a large length of time is required before this equation becomes valid. And in the meantime, if we want to describe how it's spreading as it's in the flow, we need to know the time it's been in the flow for. If we can't use Taylor, then what can we use? How can we do this? And again, Fengchang suggested that we could do some Lagrangian particle tracking. We certainly need to understand what the 3D processes are before we simplify to a 1D process. And the other question is, what do we have if we have unsteady flows? So if we have stationary flow that then accelerates, what can we do about that? So this presentation is going to look at a couple of those things. It's going to look at what we might have, what we might do for laminar flow situations which are well below the well mixed time, and what we can do for unsteady flows. So most people are familiar with Taylor from a civil engineering hydraulics perspective. At the same time, in University of Cambridge in the UK, we had another professor, this time sitting in the chemical engineering department, who was suggesting that if you want to be able to describe the fundamental mixing processes for any system, you need to be able to get this residence time distribution. And so what we've done is we've taken this approach and compared it to some of our data. And so for transitional and turbulent flow, this residence time distribution, as Taylor suggested, if the material's been in the flow for long enough, is of Gaussian shape. And we quite often present these curves, instead of as a residence time distribution, we sometimes present it as a cumulative residence time distribution. So just the sum of the time plot. And you can see in the bottom right-hand corner there, the green curve is the cumulative Gaussian response, which we would expect to get if it's transitional or turbulent flow. And then if it's laminar flow, the only thing we've got spreading material transversely or radially is molecular diffusion. So that's much, much smaller, an order of 1,000,000 times smaller in magnitude. And so we can just take the transverse or the radial profile of the longitudinal velocity, integrate that up, and that's what the blue line suggests that we should have as a cumulative residence time distribution. And that's what Dankwart said you should be looking at for simulating transport in a pipe in laminar flow. So the very simple laboratory experiment that we've got is shown here. It's about 20 meters long in total. We're looking at a 10-meter length. It's a straight pipe. It's 25 millimeters internal diameter. And we passed the pipe through the fluorimeters. And so the concentration distributions that we've recorded are some sort of cross-sectional average. And we'll come on to it later in the talk that we don't exactly know what that is. But we did these experiments, or James did all these experiments. It's been published, this work. And if we take that data that we previously had and we deconvolve it, we can, from the laboratory data, determine the CRTD, determine the cumulative fraction. And what we found, if we bunch this data together, is that for the high Reynolds number above 5,000, we do get these blue cumulative Gaussian distributions, where we get a Reynolds number that for our system was in the transitional zone. We've got these green distributions, whereby it's not quite as well defined. But what was really highlighted in our studies was that when the Reynolds number was below 3,000, when we were having laminar flow in our system, the the CRTDs followed very closely the theoretical line from Dankwart's from integrating the velocity profile. So our suggestion is that we should use this approach to predict and to route material down the channel. So this is just two plots at the downstream end. So we've taken data that were recorded almost 5 meters downstream from the injection, and we've used 3 different predictive routing approaches to see how close they are to the recorded data just over 8 meters downstream. We use Lee's model for estimating what the dispersion coefficient should be, and that gives this green distribution that is overestimating the dispersion. The improvement to that method was published by Ramiro Gomez and Choi in 2011, and that's the red curve on the plots here. Again, significantly better than the overestimated dispersion from Lee. But if you go back to Danckwerts and you just use the simple integral of the velocity profile and apply that, you get a far better distribution, a far closer distribution to what we measured. And so my suggestion is that, if we're looking at these cases and we've got laminar flow occurring in our pipes, perhaps we need to revisit the routing procedures that we should use. If we pass on then from looking at steady flow and we now look at unsteady flow situations, it's the same pipe. This work hasn't been published yet. This work we submitted for consideration just probably a month ago now, to be honest. But it's still from James's thesis, which was submitted in 2013. So it's matured. It's been on the shelf a long time. The only difference to this work is we added an additional fluorimeter just downstream from the injection, and you'll see why we did this later on when I just present some more pictures. What this study did was it looked at either accelerating or decelerating flow conditions. We set up an initial flow rate, an initial Reynolds number, and then we accelerated or decelerated the flow over different rates, so over either a 5-second period, a 10-second one you can see with the green line here, or a relatively slow 60-second increase. And we did this for 4 cases. We did from turbulent to turbulent, both accelerating and decelerating, and then we did it for laminar to turbulent and turbulent to laminar, accelerating and decelerating conditions. So there's a huge data set here, and I've just picked out a few to try and illustrate some of the results. This is a trace where you can see the colored curves are the measured distributions. You'll notice there's one missing here. One of the fluorimeters didn't work. And this is a 5-second acceleration. So we've set up steady flow and we've injected the dye during steady flow. We've then accelerated the dye over 5 seconds to a higher Reynolds number. So I think this is from a Reynolds number of about 7,000 to about 47,000. And you can see that we've captured the trace as it goes down the system. If we put all those traces on top of each other, which I've chopped off the top of this one, you can see that what we get is the duration of the trace, or the spread of the trace, is decreasing until we get to down here. And because the flow rate is increasing, it's traveling faster through the pipe, so the duration is actually reducing. And so if we've got unsteady flow, we can't use an increase in variance over time to analyze this. And so what we've done is we've adjusted the time to look at flow weighted time, so we know how the flow changes in our system. So we've adjusted the data so that we've got units of flow weighted time, equal increments of flow weighted time, and then when you put those on top of each other, they comply more like with what we're expecting, that the spread of the distribution, this is the temporal spread of the distribution, increases as you go downstream once you've accounted for the acceleration of the flow. I'm very conscious I'm taking too long now, up to 16 minutes. So the suggestion is we should be using that approach. We should be using a flow weighted time. Some results from the tests that we did, and I probably put too many results in here, so I will focus on this one and then quickly go through the others that make up the page. The gray dots are the measured downstream concentration. The black dashed line is the calculated best fit we can get to that when we analyze it in flow weighted time. So those are the data and the analysis of the data. If we look at the making a prediction at this site, if we don't do it in flow weighted time, if we do it in normal time, then we obtain a distribution, even using the best estimate of dispersion coefficient that we can get. We overestimate the dispersion because we're not accounting for the acceleration. Whereas if we do it in predicted downstream with the flow weighted time, the blue curve, it's a much better representation of what was observed. So I did put together several slides at different acceleration durations, and basically you can see the same trend. If you do an analysis or a prediction in real time, it's worse. There are two here at 60 seconds because we were able to do 2 injections. The first one with the greatest acceleration is not so good. When you get towards the end of it, it makes very little difference. So that's what we obtained when we were looking at turbulent to turbulent acceleration. The more interesting one is perhaps what we found when we went from laminar to turbulent. And again, this is the same sort of plot. The gray dots are the measured downstream concentration. The black line is the optimized fit. The red line is the prediction based on standard time, and the blue one is based on flow weighted time. Again, the flow weighted time is significantly better than the actual time predictions. And if I quickly run through these, what you will notice at the 3 plots here is that we've got a secondary bump. And this was one of those occasions when a PhD student comes to my office and tells me, this is the data I've collected. And that's not right. You've done something wrong there. The injection system isn't working. We should go back and modify it. And so that was the reason why we introduced the additional fluorimeter. The concentration is too high, but we introduced an additional fluorimeter, 0.5 meter from the injection, which shows a nice smooth distribution. And this is when we're going from laminar through to turbulent, but because of the way the flow accelerates, that all the water doesn't accelerate at the same rate, it disaggregates this pulse of dye. And you can see if you look at the green one, you've got a small initial pulse, a large pulse, and then another small one. And then once it's been disaggregated, this continues down the pipe. If we put those together on peak centered time, we can see we seem to get the same sort of effect here, but it appears in this that the third hump, the disaggregated small amount that's been delayed, doesn't follow the sequence. If we look at it in flow weighted time, then it shows that basically once the pulse has been disaggregated, then each of the pulses spread in the same manner. So we've got the main body of the tracer is spreading, and then this secondary third pulse here is also spreading in a similar manner. So this was something that we hadn't seen before, and if we've got a system where the flow is stationary, the flow is accelerating, then perhaps it's something we need to take into account in our models. So we just did again the same sort of comparisons of what we would do, but over the initial spread of the tracer. So we took the distribution at 5 meters from the injection, which is Gaussian. We compared it to the data that's nearly 3 meters downstream, and we did the routing predictions. And again, the flow weighted time predictions are far better, but none of them pick up this disaggregation effect. So we've got an issue here that in a one-dimensional model, we're not describing these 3-dimensional systems. So if I quickly run through my conclusions, and apologies for that I've taken longer than I anticipated. In laminar flows, we suggest we should use a residence time distribution approach, which is independent of time, so it makes it easier in that sense. For unsteady flows, we should be working in flow weighted time so that we can correctly analyze the dispersion. I haven't shown this point here, that again ran out of slides really, but in decelerating flows, we've just got the longitudinal dispersion coefficients are slightly lower than the equivalent steady state ones. But the big novelty, interesting thing that we saw this disaggregation of the tracer cloud when we accelerated the flow either from stationary or from laminar conditions into turbulent flow conditions. And that's what we need to look at further. And as a final slide, what we're currently building here in Sheffield now is we're building or replicating the pipe system, but this time we're building a Lagrangian tracking system for the labs, and we're going to use laser light sheets and a tracking system to be able to record both cross-sectional concentrations, distribution throughout the whole cross-section, and also to be able to track particles or concentration gradients or some of this biofilm that's been sloughed off the pipe walls. So I'll leave it at that. I've taken far too long and I apologize for that. So I'm sure there'll be questions and I'd love to discuss things with people.
Thanks, Ian. And so for our last speaker, we have Ahmed Aboukifa, who will sort of extend this into some work that he did with lead and specifically particulate lead, which has been highlighted in the past to be important. So take it away, Ahmed.
All right, thank you, John. My name is Ahmed Aboukifa. I'm at the University of Illinois at Chicago. And today I'll be talking about some of the work that I did a few years ago when I was a graduate student at Washington University in St. Louis on modeling the release of dissolved and particulate lead species from lead service lines. So I would first like to start with a little bit of background and some motivation on why we did this work. So we probably all know that service lines are those small diameter pipes that deliver water from the water main to the home plumbing. And in most cases, those service lines, they cross the property boundary, which means that the ownership of the service line is typically shared between the utility from one side and the homeowner from the other side. And that actually gives rise to what we call partial lead service line replacement in case that service line was a lead service line that needed to be replaced. And in partial lead service line replacement, the utility would just come in and then they would dig out their part of the service line, replace it historically with a copper pipe, and leave the homeowner's part of the service line in place. And they do that thinking that this would actually reduce the lead release from the surface line, but there has been a lot of studies that showed that this is usually not the case, that partial lead service line replacement may in fact accelerate lead release due to galvanic corrosion. Another important issue with lead service line replacement is that the disturbance that happens to the service line when the utility replaces its part results in destabilizing the lead oxide scales on the pipe, and that results in the release of particulate lead species or the mobilization of particulate lead species, especially under high flow events. And there's been a lot of work that showed that this release of particulate lead persists for a few months after the partial replacement of the service line. And so the objectives of this work were to, well, the key objective here was to develop a model for simulating the release and transport of total lead concentrations from service lines. So that includes simulating or developing a mathematical model for simulating the dissolution of dissolved lead, and also the mobilization, the transport and deposition of particulate lead species, and then use this framework, this modeling framework, to kind of try to understand the mechanisms of particulate and dissolved lead release under realistic residential flow patterns simulated with a stochastic water demand generator. So let's get to the nitty-gritties of the mathematical model. We first start with the dissolved lead species model, and for that we use the dynamic 2D convection diffusion equation. Of course, this is the Victor form, the full-blown convection diffusion equation, but in pipes, because we have axis symmetrical geometry, we could actually reduce that into a 2D model. So here on the left side, we have the accumulation term, which shows the concentration as a function of x, r, and t. So x and r are basically the axial and radial coordinates, and t is the time. So this is a dynamic model. And then on the right-hand side, we have the advection term, or basically the convection term. We have the diffusion in the longitudinal direction and the diffusion in the radial direction. And then using the right set of boundary conditions, perhaps the most important one of these boundary conditions is the boundary condition at the wall, which basically describes the dissolution of dissolved lead from the scale into the drinking water. And so we use two different models to kind of describe this process here. The first one is what we call the diffusion limited model. And in that particular case, we assume that the lead scale is in equilibrium with the dissolved phase, and under that condition, the concentration or the dissolved lead concentration right at the scale is going to be equivalent to the equilibrium solubility, C equilibrium of the scale. And by doing so, we're basically assuming that the dissolution reaction is very rapid and that the whole process is actually limited by the rate of diffusion of lead into the drinking water. But alternatively, we could also simulate this boundary condition with what we call a dissolution limited model, where we basically explicitly account for the flux of dissolved lead from the scale using a dissolution, using a dissolution rate function or term. And then we solve this equation using an alternating direction implicit numerical scheme, which basically alternates the solution between the radial and the axial direction. So it does it for the first half time step, it does an implicit solution in the radial direction, and then an explicit solution in the axial direction, and then it rotates, so it does an explicit solution in R and then an implicit solution in X for the second part or the second half of the time step. And the reason why we picked this is because, well, first of all, it's easy to code, and it's basically unconditionally stable under all flow ranges that we might encounter in lead service lines, and it's also pretty accurate in both space and time. Now, for modeling particulate lead species, things get a little bit more complicated because the transport of particulate species is actually dependent on several phenomena or processes like advection, diffusion, coagulation, and deposition. And all these processes are actually dependent on the particle size. And so we should, or the most appropriate way to model the transport of lead particles, or any particulate species for that matter, is by using a description of the particle size distribution function, which is basically, it tracks the change in the diffraction of the different particle sizes as the water flows through the service line. And this partial differential equation also includes advection and diffusion terms in addition to inertia and coagulation terms. We could not use this particular model in our case for two reasons. The first reason, we did some analysis on the Stokes number, and we found that for most of the flow ranges that we may encounter in service lines, particle sizes that are less than 50 microns are mostly going to be, or the inertia component is not going to be significant. So that means that the particles are going to be moving right with the flow streamlines, and in that case, it is safe to basically assume that we can simulate them as if they are a dissolved phase. The other part is that we haven't really found any studies that tracked the change in the particle size distribution, and that means we could not calibrate this coagulation function. So finding these coagulation coefficients would be impossible without experimental data. And again, that was also another reason for why we had to, again, switch to the 2D convection diffusion mass balance model, because all the experimental studies that we found tracked the change in the mass of dissolved, or the release of the particulate lead mass from surface line. So we kind of used the same 2D convection diffusion equation and solved it using the same numerical approach. The key differences here are that we added a settling function to account for the settling of lead particles from the suspended phase to the attached phase. So for particulate lead, we are keeping track of two different phases: the suspended phase, which again is simulated similar to the dissolved phase, and then there is the attached phase, which I'm going to come to in a second. And then these two phases are connected by the detachment flux boundary condition, which basically accounts for the detachment rate from the suspended phase, from the attached phase to the suspended phase. And of course, the settling adds or moves the mass from the dissolved phase to the attached phase. For the attached species, or for the attached phase, we kind of borrowed the concept of stacked cohesive layers that Javi Boxell developed more than, well, it was 10 years when we did this work. And he developed this model for simulating discoloration events in water distribution pipes. But the idea was very nice because it modeled the attached phase as a potential of accumulated particles. And that's kind of what we used in our model as well. So here we're keeping track of P, which is the potential of accumulated lead particles that could be released to the dissolved phase. So this P here, this potential here, increases by generation, decreases by detachment, and increases by settling. And then the detachment rate is a function of the shear stress, or more precisely, it's a function of the shear stress residual, which is the difference between the applied shear stress at the pipe wall, which is induced by the flow events, and the shear strength of the stacked cohesive layer, or the current layer. So basically, the idea here is that we're assuming that the particles are stacked in several layers, and that as you go deeper in the layers, the shear strength increases, which means that it gets harder, or you require higher shear stress to mobilize that particular layer as you go deeper. And so the shear strength is again a function of the potential itself. So as the potential increases, the shear strength decreases, which means that it is easier to mobilize the lead particulates at high concentration or at high surface potential than the ones that are at low surface potential. So this is kind of a semi-empirical model for the release or the detachment of, or the mobilization of particulate lead species from surface lines. Now, of course, we non-dimensionalize the models for both the particulate and the dissolved, or the dissolved particulates, the dissolved and the particulate species in both the suspended and the attached phase, and that actually gave rise to 7 dimensionless groups. I'm going to skip the details here because we're kind of running out of time. But for simulating the residential flow demands, we used a stochastic demand generation model. We developed this, or basically coded this, and this is based on the work by Enrico Criaco from Italy. And this actually was built on the work of Buchberger from Cincinnati. So this is the dynamic Poisson pulse process model, which basically simulates residential flow demands as rectangular pulses with a probabilistically determined intensity and duration. And so we aggregate these instantaneously generated demands to give rise to the flow profile in the surface line. And that actually is nice because we can then simulate different flow events, including stagnation events and different flow rates, different flow intensities. And so to calibrate / verify the model, we compared the simulation results against pilot scale experiments. And these experiments were done by Dan Gimar's group. He's also at WashU. And in these pilot scale experiments, the pipes were conditioned for almost a year before introducing different solutions or different water chemistry scenarios to see how the change in the water chemistry from the initial conditions results in releasing dissolved lead from the service lines. We basically compared the results of the dissolution limited model against the diffusion limited model. And we found something very interesting. We actually saw that the diffusion limited model gives pretty good predictions for the first almost 10 hours of the stagnation period, whereas the dissolution limited model gives better predictions for the longer term or for longer stagnation periods, particularly the 24-hour stagnation point. We also compared the results of the particulate lead model against pilot scale experiments. Here, the pilot scale experiments were done for a full lead service line and a partially replaced lead service line. And you could actually see a couple of interesting things here. First of all, that the release of particulate lead increases significantly with the increase in the flow rate, which is not surprising. And also that the release of particulate lead from the partially replaced lead service line is significantly greater than that for the full lead service line, almost 1 order of magnitude higher than the full lead service line, which basically perhaps tells us that it might be even better to leave the full pipe in place rather than partially replacing it with a copper pipe upstream of a partial lead pipe downstream. Another important thing, which I'm going to come to later, is the huge variability in the release of particulate lead, especially under medium and high flow rates for both full lead service line and partial lead service line. And that actually tells us something about how this should be better modeled, which again, I'm going to come to later. But basically, this actually tells us something very interesting, that for the same pipe, under the same flow condition, you could get a huge variability in the release of particulate lead. And then we compared, or we basically did a Monte Carlo simulation by running the model for 200 different flow realizations. So everything else was kept the same. The only thing that was variable was basically the flow events. And then we compared the results against field measurements from the literature. And these field measurements were collected from about 20 different homes in Washington, D.C. and Providence, Rhode Island. And the beauty of this particular data set is that the homes had, well, I mean, 1/3 of the homes had full lead service line, the other 1/3 had partially placed lead service line, and then the rest had an unknown service line connection. And we actually saw that the model, or the Monte Carlo simulations, are pretty consistent with the field measurements under low flow conditions, but they tend to overpredict the concentrations for medium and high flow conditions. And we think this could partially be attributed to the fact that this was a profile sampling study. So they first collected the sample under low flow condition, and then they increased the flow rates, collected the sample under medium and then under high. So by the time you get to the medium flow sample and the high flow sample, the service line had already been flushed for a few minutes under an increasing flow rate. So that could actually explain why there is kind of an overprediction here by the model compared to the field experiment. And that, of course, aside from the fact that the calibration was done on a different system than what the field measurements were collected from. But we basically wanted to see if the model is giving consistent results or if it is completely out of range. So I just want to finally highlight the different mechanisms of lead release, of particulate and dissolved lead release from the service line that was revealed by the model. So here we see an example of one of the 200 flow realizations that we had in the Monte Carlo simulation. And basically you see that the solid line here, this is the profile of the dissolved lead concentration at the outlet of the service line. And basically when you have a stagnation event, the concentration of dissolved lead builds up in the pipe. And then as soon as you have a flow event that basically flushes out some of the lead concentration, It doesn't really go all the way to zero because you still have that flux coming from the service line. Depends on the equilibrium concentration in the model. But then as soon as you get into another stagnation event, the concentration starts building up again. For particulate lead, the release doesn't really happen unless you have a very strong flow event. So here you see that we have two spikes of particulate lead release represented by these two dashed lines. And they happened for the two largest flow events during the day. And something that was kind of interesting to see, which is kind of was kind of expected given the structure of the model, was that although the second flow event had a higher flow rate, the peak of the particulate lead release for the second flow event here was lower than the peak for the first flow event. And that could partially be because the first flow event exhausted most of the particulate lead potential, and then the generation function didn't really generate enough lead to completely replenish that kind of reservoir of particulate lead. So that's why, so that kind of explains why we see this lower peak here in the particulate lead release, whereas the flow event here was higher than here. Another interesting part was that if you track the mass of leads that was released in any or in each of these, or particularly this one first flow event, the mass of particulate lead is about 400 micrograms from the partially replaced lead service line. And if you compare that to the amount of lead in a paint chip the size of a penny, it is kind of higher than this. So imagine how much lead would that be if you use this water, if for cooking, or if you drink this water. That would be an enormous amount of lead. So this kind of concludes my presentation today. I kind of wanted to touch on some of the limitations and plans for future development. So if you remember, perhaps the most significant limitation of this work is that the way we modeled the particulate lead release was based on a deterministic description, but we could actually see that there was a huge variability in the release of particulate lead species, particularly from partially replaced lead service lines. So again, for the same lead service line, for the same flow conditions, the release of lead species significantly varies from one sample to another. And that probably tells us that we need to change our model or expand it so that we kind of have a probabilistic or stochastic descriptors for the generation and especially the mobilization of lead particles under different flow regimes. And perhaps another limitation, of course, is that the model requires extensive calibration. So we had to get all this pilot scale experimental data sets from the literature to calibrate the model. And there is also a little bit of discrepancy because the data set that was used to calibrate the dissolved lead model is different from the one that was used to calibrate the particulate lead model. We couldn't find one complete data set that tracked both. At least at that time, I didn't find any studies that did that. So that also is another limitation of this study. But that kind of concludes my work, and I would like to thank my PhD advisor, Dr. Pratim Biswas at Washington University in St. Louis, and Dr. Dan Jamar at WashU, and the US EPA for funding my PhD work. And thank you.
Thank you, and thank everybody for sticking with us. Obviously, we sort of went over on time, but I think everybody hopefully got something out of the talks. I certainly did. I found them very interesting, and again, thank all the speakers for their time and their effort in putting this together. And I will work with our group to consolidate any questions and work with the the speakers to get any answers that might be outstanding. And you can reach out to Junseok Lee, who's our task committee chair, for any other questions, or if you were forwarded the invite, you can be added to the list. The other thing that I want to say is that we have the operations webinar series that's planned for October 27th. Thanks, Bill, for updating that to the slides. So hopefully we'll see you there in a month. And with that, I'll end it. And again, reach out to the speakers or myself or Jun Suk with any questions. So with that, I'll conclude. Thank you.